welcome ladies and gentlemen to this video. Today I wish to just keep a vlog about the different progress that I've been engaging, or the different progress I've made in the development of different robotic parts. I've got a bunch of different projects and lists, to be honest, that I like to pursue, and I just want to keep a track of the different things that I've been working on. So here, this is the work that's been from about the end of April to through May. I've been working on this series of projects that we're going to go through next. This video is going to be about 30 minutes, maybe, if I get there, or at least 20, because there's a lot of stuff. Anyway, so let's start with this one. This is a cyclodal drive that I've been working to try and imply pulleys in the cyclodal drive. Now, why do I do that? It's because I believe that if I add the string with a good amount of tension, I can embed a series of suspension inside of the gear mechanism, so to ease the transition between teeth. Now, that might not be super effective on the cyclodal drive, but it can also help deal with inaccuracies in terms of lobe shape or intersections, meaning that it's a little bit more easy to make the system behave properly. Now, it's still a nascent idea, however, I thought it was interesting enough to try it. So what I did is I created this lobe here with the right geometry to make it work. This is a 9:1 gear ratio. I initially started with a pin diameter of I think it was 10 millimeters, but then I switched to simply use bamboo skewers as the pins because it would create a very sturdy assembly mixing bamboo and 3D printing. So I just used the diameter of the bamboo skewer itself. And then what I did is I adjusted the position of those circles so to fit. It's kind of a tricky thing, but it's still possible. And so I adjusted the thing to fit the system, and then I wrapped, so what I did is I distributed 9 of those pulleys around, and then I wrapped a string around in each of these 3 channels. These 3 channels create kind of a belt around the inner lobe, and the belt will kind of indent or move inwards as the system goes around. Now you might say I'm going to lose efficacy, but it also helps guide the system and provides a suspension, so it runs very smoothly. There is no direct contact. It's a kind of a slow progressive contact, which I think is very useful because I think the string can really help turn this motion into, instead of a hard push, into a kind of a more of a sliding or soft movement. So I think there's something really beautiful about that. So I printed that. It's right next to me right here, and it's functional. I've got a bunch of different gear sets behind me, and it's really something beautiful to watch. So that's what I did for the cyclodal drive. These are the parts. I printed a bunch of those to make it happen and assemble it, and it works. So let's put the cyclodal drive aside for the minute. Let's move on to the next one. This is a very interesting one that I've been working on too. I put that aside for the minute though, because I don't think it's the most useful for now, but it's still in the back of my head about how to use that properly. So I thought about how to create systems that have bendable parts, so that I can create a flat part and then bend it into shape by using string tensions in order to tighten the thing, and then create the 3-dimensional volume from a flat shape. Now, what's the advantage of this in 3D printing? It's because I can create plastic suspension or compliant mechanisms or systems that utilize their flat 2-dimensional geometry in order to provide stability to the greater structure. And in doing that, I was trying to create an icosahedron, which is 3-dimensional shape made out of triangular pyramids. Much like the dodecahedron, but the icosahedron is a little bit different. It's a 20 triangular prism laid out in a shape. It creates a sort of a hexagonal 3-dimensional shape. And so I thought, if I reduce that and I try to find just one corner, what pattern should I use that I could, on a flat surface, that I could then bend using string in order to get the right corner for that icosahedron? Now, that's a complicated thing to do, and I thought maybe I should try first, before knowing how the folding works on 3D prints. I should try to see if I can translate sewing patterns into 3D printing first, so to test different properties of the way the plastic bends. So this is just the first test I did in that line of thought. I didn't go further in that, but it's still in the back of my mind. So I made a bunch of different patterns here, and I tested them and see their properties as they flex and bend. And I have to say this is very promising, but it's not at the forefront of my mind right now. I've got other things that I'm pursuing. Anyways, so that's one of the things I did. Next up, the next one I want to go over is this one, which is another magnificent idea. This is something I call paper frame prints. I call them paper frame prints for a reason, and you're gonna understand why in a second. So I thought about origami and how origami is part of engineering, so to develop many different systems, and it's a beautiful thing. I mean, origami, you can go to extremely high levels of complexity and mechanical properties of paper. And so I thought, what if I cross origami and 3D printing? What could I achieve? And so I started to think about that, and I thought, if I want to create a system of origami and paper that would be coherent, I also need to develop a system that enables me to create predictable folds in the paper. So if I create a system of predictable stamps, then I can produce reliable objects that will always have the same behavior. And so, or the same shape of paper, and then I can cut it to size and put it into my print. Or I can even design a stamp that would be shaping the paper just by pressing it and then cutting it to size all at once. So I thought I'm going to start with that, and so I created a bunch of different primitive stamps so that to impress a shape on the paper and see which one works and which one doesn't. So this is the first set of stamps that I made. I had a bunch of others, I think, but yeah, so this is the second set of stamps that I made. Now those ones are interesting when it comes to trying to give structural qualities to the paper. So if I want to make something like a roof or a bridge, this enables me to create a corrugation pattern on the paper that gives a structure to the paper. So if I have like a bridge or a roof or two distant pillars I want to relate with the sheet of paper, if I use those stamps to imprint the shape on the paper, then I can enhance the structural qualities of the paper. So this is a useful thing. These are different experiments so that I could see which one works and which one didn't. I based this on a vector sketch. So maybe you'll see here. So I had all these different patterns that I decided to try and see which one functions and which one doesn't. I didn't try all of them. I tried only a few. And then I noticed some improvements and some other things. Now I put that project aside for the minute. It's still in the back of my head. I'm just not pursuing it directly. But there is a lot of promise in there. You can get a really high level of atonement. The thing is, I figured out that to pursue this line of thought further, I need to have a much more refined level of understanding about how to create those predictable stamp patterns. Because I need to actually elevate the production of those paper folds to a robotic assembly line, like you would see in a manufacturer somewhere. In order to produce the right piece of paper to be predictable every time, like the assembly line for it is extremely complex. It's no simple thing. These little stamps make a nice difference, but if you want to have a predictable thing, it requires big investment and effort. So that's why I put it aside for the minute. It would be like a project that would take a year to develop that thing. So let's put that aside for now. Now the third experiment I wanted to make with the paper frame prints for the stamps was a radial system, because the fan, so one of the ways I wanted to use the paper frame prints was to create a suspension out of a fan folded piece of paper. So if I have a long piece of paper and I fold it in regular increments, then I can get this piece of paper that has this suspension quality to it, where when I press it, it bounces back up. So if I want to create, say, a tabletop figurine that's 3D printed and also have suspension embedded in the joints, then I could create these little fans in a circular fashion and then compress them and then expand them as I need. It would create inherent suspension within the 3D prints. So I created this radial pattern. This is a testing print. This is not a final print. I wanted to see what was the right extrusion necessary to get the right folds, and I figured out that at 4, this is a 4-degree extrusion, I think. No, that's 3. Okay, so 3 degree. This one would just tear the paper, so it would create a cut through the paper, and those ones would not register. So I had to settle for something like 2mm extrusion to get a noticeable fold. Now this is not the best way to go, as I figured out this system and the way the teeth is made. This makes the paper tear, so I can't really use them to create predictable motions. So instead I had to go into a more gear oriented press system, so the rolling stamp. So because I wanted to keep it simple at first, I just took a spur gear outline, and with a rather large tooth size, this one is a modulo 2, and with the larger tooth size, I would just pass the paper through 2 intersecting gears, and it would create this corrugated pattern naturally. Now, because it's a rolling stamp, I can also process a whole page rather effectively. So that is the current system that I'm using to create those folds. However, this, like I said, this system needs to be improved. It's going to take like a year just to get it to the right level, and it can reach absurd level of complexities. So that's going to be it for the paper frame work that I've been doing. Well, no, the last one before for the paper frame. I also needed to have a way to connect the paper in ways that are ever more efficacious, because there are structural properties that are inherent in paper that are not part of other materials, and so I'm trying to figure out ways to tie them right. So this one here, I have slits in the center and slits at the end. It would enable me to pass the paper and then pass a pin or a string through it. So that way, if there is any force applied to the string, it would not tear the paper, but it would only apply to the plastic, and thereby I could have a steady connection without destroying the paper and still apply a decent amount of force and maintain the structural quality of the paper. Because if I relate 2 of these parts, say if I put 2 of them side by side and I relate these 2 ends with a piece of paper, then I can get a joint that folds and goes around quite easily, yet has quite a high amount of tolerance for a certain direction of movements. So the paper does have some really special qualities. But here I needed to test what was the right size of slit, so to put the paper in, that would also print without issue. So I have different sizes of slits, and it turns out that 0.3 seems to be the right size. So when 3D printing, I think you should never go below a dimension of 0.3 millimeters. If you're going below that, you're starting to play with dangerous issues, meaning that your print will likely fail as a consequence of printing failures or inaccuracies, or I don't know, the motor didn't work right on that layer and everything messed up. So if you go with 0.3 as a minimum dimension for anything you want to make, you should be fine. Okay, so that's gonna be it for the no, I actually have 2 more for the paper frame. This one here is a very functional joint. So this is a knee joint that is using paper frames. So this cavity in the center here is meant to, you put it in a piece of paper that was folded, like a fan. You slide it in so you can tie it to one side using these holes and glue. So you can pass a string, wrap it twice, put some CA glue, and then tie it in the back. That's how you tie the thing, and then you let the fan be on one side, like you see here, and as you fold it, then the compression will act as a suspension. So I have 2 slides, so it's 2 fan piece of paper, and as you fold it, it's going to spring back into shape. So this is a very functional joint. I'm wondering what I can use it for. I'm thinking about creating a small figurine size robot, but I've got other projects that have come to the forefront now, so this is a little bit in the back of my mind. It's not really at the forefront. I'm kind of satisfied with what this is. It serves the purpose that I wish. I can also put that in the finger of a robotic hand, so that I can have the spring from the contraction of the tendons, which would be very interesting. But so that's in the back of my mind. I also made another one, which was the elbow joint. Now, but this one this was more of a test. I'm not sure where to put the the actual paper. So this is just a joint that has a higher degree of freedom. So it's a three-dimensional axis, spherical axis. So, but yeah, there's no paper in this one, so I still need to figure that out. Okay, so that's gonna wrap it up for the paper frame, which is a kind of a big step forward in my thinking about the printing. Now let's go to planetary gear systems. So I was thinking about creating this planetary gear system by adding pulleys into it. So I've been doing this with the cyclotron drive, as you saw at the beginning of the video. And now I was wondering if it was possible to do the same, but in a planetary gear system. Now, what would be the advantage of that, since the string is going to add an efficacy, kind of a lack of efficacy because of slippage and resistance, which are very good ideas. The thing is, I still think it's possible to utilize this to a great benefit, because if I use pulleys, it's like adding a belt inside of the gear system, meaning that I could also drive the belt to add torque and power to the engine as it spins. It might also help stabilize it as it goes to higher speed. You could do something like change the contact points at low RPM and high RPM, so that the gear at low RPM would utilize the teeth, but as it expands, or as it speeds up and expands, maybe dilating the outer ring would enable you to run the whole thing with strings instead, meaning that you could reach much higher RPMs, because the circular nature of the belt or string, as compared to the teeth of the gear, I think enables the object to reach much higher level RPMs with less tear, because the shapes are less conflicting. So that's why I thought it was a useful pursuit. Now I tried to print this and it didn't turn out to be a good print, so I have to think about it again. But I still think there's a lot of useful things that can be done with that. And so in the pursuit of that, I decided to create this planetary pulley system. Now I just created, you don't see the full assembly here, you just see the pulleys. I have it in my hands over here. Not sure if you can see that. Kind of a small thing, but this is basically, I printed 3 of those. 3 of the big pulleys and 1 of the small ones, and I'm trying to figure out the right weaving pattern, so to connect the outer pulleys to the inner pulleys and have an extremely high level of friction. So if you consider the fact that the issue with using pulleys in a planetary gear system is the slippage, well, there's ways around that, and one of the ways around that is to have a very high amount of friction or wraps around the different pulleys. So if I wrap once, so if I have, say, the big pulley, and I wrap full turn and then go to the center pulley and then do that for each of the 3 pulleys on 3 different levels, then I have a lot of friction that connects the outer pulleys to the inner pulleys. Now there can still be slippage, however the level of friction is so high that it does circumvent the issue. And what happens is that because this is a circular diameter from the pulleys that are connecting, it allows you to have a much higher level of fluidness, meaning that the system can run at extremely high speeds and it doesn't really matter. And I also think that the slippage can be actually a benefit or a beneficial thing. So if you have some large power difference, or there's a torque issue, or it's like a jerk in the engine type thing, the slippage, I think, can be an advantage by reducing the stress on some part of the system. So I think the slippages can actually be an advantage, but it depends how it's used. Now this is still in development, so I'm not exactly sure how it's going to grow. I just thought it was interesting. Okay, so now I'm getting into the much more recent things. One of the things that are interesting, I think I'm going to finish with this one. I've got 2 projects that are worth expressing here, so I'm going to go there. Well, 3, okay, and that's going to be it. So I'm trying to figure out how to print how to print a plane, basically, or a small bird, more like a hawk, to be honest, because I like I like the nature aspect of it. I tried to create this fan and this duct to go over. That's going to be the forward propellant. Now this is going to be the first layer. So if I think about a bird has two or three layers of feather. So that would be just the leading edge of the feathers. Now there would be also a few different feathers following, which made in a different file. I'm not sure where it is. I printed that yesterday, just I'm not sure where it went. Huh. What happened with that? Hold on, I'm just gonna pick it up from the desktop then. So I created this feather here. So this feather is going to go inside of this. So you can see that there's three holes here, which will connect with the holes over here. So that's going to enable me to spin the feathers and bring them closer or out. So that's what it's going to be used for. So that's going to be just the first part of the wing, and then there's going to be a set of feathers behind them that have mobility, so it can move. So that's still in development. I mean, I spent just a few hours on those. I tried to also create an ornithopter for small motors that I have, which is going to be, ornithopter. That's going to be kind of using the same things, which is going to be kind of interesting. Now, this is just about it. Printable belt. That's interesting too. If you want to print belt directly for some mechanical assemblies, I think that's really useful. So there's a few dimensions that are useful in here. You don't want to have more than 1 millimeter by 1 millimeter square extrusions for the bendable belt parts. I'm using a water wash resin plus. So if you have a frame member that has 1 millimeter square in terms of surface area that you do your extrusion from, that's going to give you the right amount of bend if you want to create a circular track. So you can actually print a flat piece and have it bend around a circle. And then I have these little ladder-like structures so that the pulleys or other systems can latch onto. So if I have a pinion and gear, I can use this as the slider. But I can also bend this after it's printed to the right shape that I need. So eventually I'm going to embed that into three-dimensional mecha geometry. So it's going to be a part of a printable piece that will have its own cavity to move within. So I'm not going to have to do any assembly. It's going to be part of the mechanism. But I still need to consider how I'm going to do that exactly, because that can grow in many different directions. Now, the last project, which I think is magnificent. Let's go back to the start. This is the biomimetic wrist of Theseus that I'm working on. This is sumptuous work. So I'm starting with some, you can see the sketch here. My objective is to bring Michelangelo and Raphael's work to 3D printing by making them as operable robotic parts. So I want to translate the beauty of those drawings into a three-dimensional limb that has a function and that actually looks like the real muscle, but can also be functional. So I really want to speak to the aesthetics of robotic parts here. I don't want to just create a robotic part that functions. I want to create a robotic part that is the most beautiful robotic piece that also functions. So I want to draw out the characteristics of muscles as you might see them in cartoons, with exaggerated muscles and very strong features, and use strings in order to activate the muscles. So I created this system here. It's going to be weaved with strings, so to create an outer shell that will look like the muscle structure. And then I'm going to add other decorative pieces to make it work. Now you can see that the connection points here relate from one end to the other, like the radius and ulna bones. So the bottom part is the ulna and the top connection point is the radius. So I still need to make the connection part for the end here. It's going to be a spherical joint for the radius, and the ulna is already present. So I did already print the first few parts, which I have over here. I'm not sure if you can see them. So this is just the bare bones, which I think is very interesting. And also you can see in here that I'm implying some of the other features that I've been speaking about in mecha geometry. I'm using mecha geometry because it's the best possible way to describe what I mean to say. Here are these two different pieces. So let me take this out. So these two pieces are very interesting. So here, this is an effective use of the mecha geometry I've been working on. So the printable bearing geometry is actually present in here. So the geometry, these are actually a series of discs that go along an axis that is in the outline of the wrist. But this axis here supports these pulleys that have this fluting pattern inside of it. And the fluting pattern enables these to be pulleys and spin around it. So if I want to have a musculature or muscle that is activated where the wiring passes through the wrist and arm, I can create this geometry at the wrist and elbow that uses these pulleys in order to sustain the mechanisms. So I've got these patterns here. These are made in order to reduce friction and enable these pulleys to pivot. So I've got them printed over here, and I can confirm to you that they do spin around. These are functional pulleys, which is kind of cool because now I can lay them out in just about any geometry that I want. And so I can create very organic shapes that have still these properties, mechanical properties, but that are directly embedded in the geometry. This enables me to have basically zero assembly time. I can just print it and then it works. So it's quite amazing. So now I printed those two. I'm gonna keep on working on those. This is what's on my plate for the next month or so. It's gonna be, I've got a vision in my mind, too difficult to describe, but it's gonna be sumptuous, something that you see once and you never forget. Anyways, so that's gonna be it for today. Wrapped up the explanation of all that I wanted to speak about today. So thanks for your time and attention, and I'll see you guys soon.